Good afternoon, everyone. I'm Margaret Mantor. I'm with the California Department of Fish and Wildlife. And today's lecture is part of the Conservation Lecture Series. You can view the schedule of upcoming lectures, register for them, watch videos of past lectures, and sign up to be on our mailing. And just to give you a preview of the schedule, these are the two talks that we have coming up. We're going to be having a lecture on bay checker spot butterfly, December 2nd. And then we're going to be having a talk on the invasive brown marmorated sea bugs, which are all over Sacramento, January 25th. Hopefully, map design, we'll see. But today we are really happy to have Dr. Brian Kluwer and Lauren Hammack presenting a lecture on the development of multi-threaded wetland channels and the implications. Brian is a fluvial geomorphologist with the National Marine Fisheries Service. He received a PhD from Colorado State University in river mechanics after completing his master's at Northern Arizona University in geophysics and groundwater. He came to NIMS in fall 2000 from the National Park Service Water Resources Program, where he worked on stream flows to protect physical processes and ecology downstream from large federal dams in the west. NIMS, Brian has worked on sediment-related issues across the West Coast. He's authored gravel mining guidelines for conserving salmonid habitat, served as an expert witness on Klamath River hydro, and co-developed sediment transport software to assist in dam removal decision-making. Recently, he has turned his attention to ecosystem linkages with geomorphology and habitat forming process. And Lauren is the principal geomorphologist at Prnesky Chatham, a small ecological restoration firm located in the North Bay. Lauren completed her master's degree at Colorado State University in Watershed Science. And prior to moving to California, she conducted field-based research projects to quantify stream flow requirements for maintaining river resources in national parks across the Intermountain West. At Prnesky Chatham, she specializes in stream restoration, science, and design. Some of her most recent projects include development of the state's first community-focused stream flow restoration, replacing water diversions with rooftop water harvesting and storage, designing a fish passage project in the Russian River, and preparing salmonid habitat enhancement projects in the lower 10 Mile and Garcia rivers, all of which were at least in part funded with the Department's Fisheries Restoration Grant Program. So thank you both so much for coming today. I'm going to go for you.
Start us off real quick. Good afternoon, everybody. I'm hoping the talk that I was asked to give from Lance, I gave at the Salmonid Restoration Federation workshop back in early or late March of this past year, and it was in a session that was hosted by Brian Kluwer and Tommy Williams of the really fascinating workshop. It was well attended, and minute talk, so I didn't feel like I had quite enough to give an entire hour-and-a-half lecture here, so I actually asked Brian Kluwer. Before I go into the details of we've got quite a big agenda here today. Quick agenda so you know where we're heading, and then I'm going to turn it over to Brian. Talk about riparian wetland losses throughout the state of California, different channel types. We're so used to seeing
Good afternoon, everybody. I think the microphone's about right. Maybe up a bit, like that. Well, it's a pleasure to be invited here. I really appreciate the opportunity to talk to colleagues and people with pretty much the same mission. And particularly want to perhaps don't get the support or the travel budget they need to attend conferences. Bringing in speakers to a lecture series like this is all right. So Lauren gave you our agenda. I'm going to start with something that maybe not everyone in the room understands, and that is what California habitat once was compared to what it is today. And I put together these drainage area slides several years ago. So this is California's salmon habitat. All the watersheds that have a connection to the ocean. We looked at the various infrastructure and development on the land that has reduced several slides here, just looking at the quantity and area of habitat that was once available to salmonids compared to what's available today. So the first biggest disconnection of major watersheds is dams, and then there's other dams. That's in the blue area, and between the dams, there's about 30% of the habitat has just been physical. We also then looked at partial hydrologic barriers in watersheds. Before that, those were total barriers, so we looked. Those categories were down to about half the original habitat. Then looked at temporal and partial barriers, depth barriers, velocity barriers, water. And those bring us down to, somewhat less than half. Then we have to look at stream flow impacts. I mean, face it, we kind of live in the desert here, at least 6 months out of the year. An altered state are probably. So we looked at areas using the state water rights database and plotted those up, and that really took a chunk out of viable natural habitat. I'm going to come back to the valleys because I think that's most important, kind of the missing piece in. So these yellow areas are what's left undisturbed in 2010. And it's kind of an alarmingly small amount. It's about 15% of the original area. Many of you who know about the forested areas, you'll recognize that these yellow areas are So back to the valleys. The valleys are really kind of the focus of the presentation that Lauren and I are going to give you today, because really unparalleled richness in our product. Great paper. I recommend you read. If you don't have it, it's short. It's got good graphics. It's just. And this is a series of decadal updates on conditions of wetlands. And in particular one, they highlighted wetland losses in California, and there's some really compelling text in this right here. So by the 1920s, about 70% of the original wetland acreage had been modified by levees, drainage, and water diversion projects. That's California's Central Valley. And then in the 1930s, large-scale flood control projects at diversion dams, water control structures were being built on all the tributaries entering the valley. Also, they point out that the two most notable projects in the United States that affected wetlands are California's Central Valley Project and the lock and dam system of the Mississippi River. So that's a scale of impact that not many people really appreciate. So what is the history of valley modifications? How did we do it, and what does it look like? I see quite a few young faces in the crowd. You probably never saw a steam-driven drag line. There's a picture of one there. And out of this same paper, the USGS water supply paper, we've got a couple maps of the former wetland, lake wetland complexes of the Central Valley today. And they point out that prior to the mid-1800s, about 4 million of the 13 million acres that make up wetland. How many acres of what we call wetland out there today is accessible and available to salmonids? So here's, for us graphical information takers, here's the maps. You can see the darker green is those areas that have reduced by 85% or more. They're wetlands, and California ranks right up there with the Mississippi Basin states as having manipulated or how did we do that? You kind of have to go elsewhere because it's already been done here. So in the La Grande, Oregon Basin, you can see from the air some really wonderful examples of kind of the first wave of how you separate a river from its floodplain. You take the meander bends, you make straight dredge channels between them, and then you line them with levees. And so that's what we see on the landscape here all over the Central Valley, but that was done long ago. It's still going on in less developed parts of the West. The history of landscape modification is also poorly documented, forgotten by many, and not even known by those of us in this generation. But it's kind of our European heritage. This is how we developed all over Europe. We brought those ideas with us to the Americas, and we concentrate on valleys because that's where the richest farming soils and opportunities are. Now, one thing about that you may not realize even occurs unless you're a farmer or grew up in that community, and that's tile drains, tile drain networks. So all the furrows in this field are a network of drains that are all interconnected. They're planted about between 5 and 8 feet deep in the soil, and their intention is to drain the soil so that crops can be grown uniformly across the entire acreage of that field. There is millions of miles of tile drains in our alluvial valley. We know that tile drains are going in the wine growing country, for example, in Sonoma. Water. The reasons for that from an agricultural perspective are to make every acre on this field uniform and easier to farm, so you can just have simple farming practices. The difficulty, though, is those wet spots, those marshes, those wetlands are the lifeline during the summer period for nearby. Here's an example that I found just recently in northeastern Nevada. This is neighboring watersheds. They're literally right next door to each other. You see the one on the left has much more green in it, but it also has a straight line running down the middle of it. That's a flood control project coupled with an irrigation scheme. Really, this landowner gets more wild and developed neighboring watershed, but look at the differences in habitat. The wildly meandering stream that has water in it during the dry summertime. Not a channel left except for a flood drainage channel in that development. kind of the business model for alluvial valley. So the valleys, what were pre-settlement habitats like with respect to salmonids? To find out today, we do historical ecology studies. And many of you are probably familiar with SFBI and their historical ecology work. This is all the study sites where they have conducted historical ecology studies or they're in progress. And what they find in their studies, these are their conclusions. Most river systems had major wetland complexes that provide variability in timing and depth. That's in terms of wetted habitat. That support diverse life history strategies that were reliable habitat and refuge during climate extremes. And here's an example. Many of you are probably more familiar with their work than I am. This is the Bay Delta area. There's the historical picture on the left. All the blue and green and yellow is wetted habitat. And on the right is the current condition. There's very little. We've done that everywhere we could that there was good climate and good soil for high value farming. Got some unexpected animations in here. Keeps advancing on it. So, you know, we're just learning. This photograph is from this research that Carson Jeffers did in 2007. That's not a decade ago. We're just learning the importance of floodplain rearing for salmonids. At the same time, we've already lost our floodplains to salmonids. So we're in kind of the crosshairs there. So working with a colleague named Colin Thorne, he's one of the world's top geomorphologists. He did a sabbatical here in the U.S. at my office a few years ago. And at the end of that sabbatical, we put our heads together and we thought, you know, I think enough is known about ecology, and we can dredge the literature and educate ourselves because neither of us are ecologists. I think enough is known in ecological principles that we could dovetail ecology to stream channels and stream channel distribution that those of us in manage of. So here's the paper published in 2013. I'm going to go through the paper. It's basically in two parts. The first part is geomorphology. I'm going to warn you now, there's some dense text. We're not going to go through a lot of it. If you can get through that part, you're going to really like the second part, the linkages. And then you're really going to like Lauren's presentation because it's almost all pretty photographs. And then I'll wrap up with the management and restoration implications of that paper. So to give you a little bit of background before we get started in channel evolution, there's a continuum of physical processes, sediment transport, hydrologic regimes, vegetation, slope, climate, that create a whole range of channel pattern types. And we've focused, after we developed all of our alluvial valleys, we have focused on types. The straightened, sometimes they're still meandering. Mostly we haven't even got any experience or any ideas. Natural wild alluvial streams. So with that little bit of background, I'm going to go through the history of channel evolution models. It was an interesting set of scientific work done in the early 80s, starting with Stan Shum and his colleagues. We're looking at incised channels, so a small set of the whole range of channel types. They were looking at and just this concept of over linear distance, you see the profile here on the bottom, you have different stages, different evolutionary stages. As the stream responds to dredging, straightening, this is kind of a powerful tool for geomorphologists. You may have heard your fellow or your favorite geomorphologist say something like, well, I think the stream is on a trajectory of. The way we have sort of developed that thinking framework in geomorphology is by understanding the trajectory of streams evolving from one state to the next based on the forces that are going out in the field and looking for those different states at different locations in the watershed. Again, with this channel evolution concept in mind, we mentally substitute space for time and give you our prediction of what we think. So this idea was embellished a bit with by the next fellows, Andrew Simon and Cliff Hupp. We thought vegetation had an important influence. They advanced channel evolution models a bit. And then my co-author, Colin Thorne, in the late 90s, he found that the channels actually expand beyond their inside, develop in an inset way side channels and proto-floodplains. So he immediately began expanding this rather confined concept of incised channel evolution. So for 3 decades, we've been using channel evolution models in geomorphology. So Colin Thorne and I both thought that physical processes that form channels occur over such a continuum of scales and time and magnitudes that there must be successional stages, and those successional stages would have corresponding attributes. And we see evidence, if you go to high latitudes or high altitudes, you go to places where my ancestors channels that have not been heavily manipulated. And this is what they look like. They wander all over the place. In some cases, it's hard to even define what is historical geology, historical ecology. In Europe, Phil Sear has discovered that in plexes in locations where David Montgomery and Brian Collins in the Pacific Northwest have found the same thing in excavations they've wetland complexes with interconnected channels. Really important work done by one of Walter in the eastern U.S. They did excavations in the very valleys where channels that those scientists had developed the channel geometry and the bank fold flow. Actually in old mill pond deposits that had incised when the mill ponds they didn't really understand what they were looking at, and it's totally influenced our concept of what. So here's where it's going to get tedious for you, and you don't need to squint and even try to read this. You can get a copy of the paper, and I'm going to interpret for you what I think is important today. We took the single thread channel. We took the channel evolution models, the first one of Shum and the next one that followed from Simon and Hupp, and we organized them and adopted pretty much verbatim what those fellows had done. And then we added 2 stages at the beginning and 2 stages at the end, and those stages are our floodplain complex wetland streams, multi-threaded channels. Linked them all together and drew it in a circle because there's no beginning and there's no ending to channel evolution. A channel can incise and recover, re-incise and recover, and go through many, many processes in geologic history, many cycles in geologic time. And channels can also get arrested in their form, and we see that a lot, particularly in the coastal channels. Of course, you see it in all. Not going to evolve because they don't have coastal channels in alluvial valleys, or coastal watersheds in alluvial valleys. We're seeing very much the same kind of mountainous channel forms that are arrested by the stream incising into very deep and entrenched of the classic incised channel, but they're not dead ends and the short circuits over here. So the stream evolution model highlights two ideas. First, we changed the name from channel evolution to stream evolution because streams are not represented just by their channel. Streams are all the processes occurring across the valley and in the watershed upstream. They're a web of bio and geophysical process interactions. And channels are just a snapshot. So we think it has broader utility. It certainly has a broader definition than just incised channels. It applies to all alluvial valley settings. It emphasizes watershed scale interconnectedness of sediment, vegetation, and hydrologic regimes, valley stream system processes and outcomes. Where do stage zero streams occur? They occur over a wide range of scales and locales. And where do we find them today? Watershed cartoon, you can imagine it scaling up and scaling down. Mountain meadows have really good remnant stages. Valley with a watershed above it. Wetland complexes with a network of small channels. Erosion to occur. They're odd because they occupy often the whole valley width. It also makes them resilient to droughts because they're full of water. Classically, at the large watershed landscape scale from the stage zero streams in the mountain valleys, which I just pointed out, alluvial fans are an example that people don't often think about. But you know what we've done to our alluvial fans. Mostly we've trenched them, made them into high-speed transport zones so that we can develop on their banks. Sediment regime, instead of that alluvial fan being a depth zone, we're now transporting those coarse sediment loads out into our valleys where our high-value wetland meadow systems. Transfer zones, the big alluvial valleys, that's the classic big location for stage zero streams. So part two, this is where I like to think the biologists get more excited. And it's linking habitat and ecosystem benefits to hydrogeomorphic attributes. Building on principles of functional ecology, we linked the stream evolution model stages to habitat and ecosystem benefits. So I'll go through the physical attributes. We first cataloged and ranked all the physical attributes. We then did a crosswalk and linked up the habitat and ecosystem attributes. Base flows, floods and flood pulses, and their timing. Natural timing is better than period or the duration of inundation. Attenuation of floods and recharge of aquifer. Geomorphic attributes, channel dimensions, geometry. Portion of shoreline that's stable and unstable. Floodplain attributes are important in this scheme. We looked at the extent, the size of the floodplain, and the connectivity. On the floodplains, we looked at sediment storage, carbon sequestration, and nutrient processing capacities. Vegetation plays an important part in this scheme. We look at the presence of plants, be they aquatic, emergent, riparian, floodplain plants, production of leaf litter, large woody debris recruitment, tree trunk recruitment, and riparian succession. Is the landscape still dynamic? Is there succession going on, or is it stable and static and has reached? Habitat and ecosystem benefits, and these are the attributes that we portion of native plants and first edges, or are they looked at droughts and water table connection? And so each stream stage is associated with the continuum, that gradient of hydrogeomorphic processes, attributes, and ranges and qualities of habitat and ecosystem benefits. And we just did an and here's the tables that are so dense that even in a couple times, and we're going to look at just a couple of these boxes. And I actually am going to read a little bit of text here. So let me back up. You notice in the on the left here, we've got the stream evolution model stages, and I've already collapsed it down to just 0, 1, and 3. Across the top, we have a column for hydrologic regime, ecology, and vegetation attributes. And I want to compare, just for example here, the information in our scheme. So for the stage 0 stream, under hydrologic regime, its attributes are floods are diffused over the full width of the floodplain, so flood peaks are maximally attenuated. Hardly even any notice of a flood peak. Flood pulses are diffused and subdued. There's a high water table and close connection between the streams. That ensures reliable base flows and continuous hyperesis. Through flow in smaller antibranches may be ephemeral. So compare that to, let's say, attributes in the hydrologic regime are concentrates an extreme range of flood peaks. All the floods stay within the banks except for gating flood attenuation and further amplify. Several more attributes in all of the stages. Tables. Table 3 is format. And I've zoomed your habitat for that same stage 0 stream. Its attributes are multiple channels, islands, and broad floodplain. Access to a rich palette of diverse habitats in close proximity and refugia across a wide range of flood events. There's a high wall. Channel margins evolve semi-continuously to exposed tree roots. And if we go down to one of the degradation destroys the benthos, removes features that provide in-channel habitat, and scour and disconnection from the floodplain mean that we gave them a score, and we added it up. Attributes table, providing over 90% of attributes to providing in the single digits, about 8% of the attributes for the look at one more example here of what's in this scoring scheme. We looked at shoreline length and complexity. The next few length and complexity is a rather simple thing, but very important to quantifying habitat. This is not a defined channel, but it has tremendous floodplain connection, long hydro period flooding on its floodplain. Compare that to this, which is not a bad looking channel, but it scores as a 1 because it's straight, it's minimum length. So that's how our scoring scheme worked for each of these attributes. Then we did the habitat and ecosystem benefits scoring as well. And you see that they line up very much the same way. You get really low values of providing habitat and ecosystem benefits in the deeply incised streams and very high values of providing habitat and ecosystem benefits in the floodplain connected streams. So on this geomorphic framework, the sort of circle diagram, we overlaid the results of the attributes scoring scheme. And so these bubble diagrams are showing us two things. First of all, the size of the bubble relates to the percentage of benefits it's providing. So a really big bubble is a lot of the benefits. A really little bubble is not very many benefits at all. The number of colors of pie in the bubble relates to the attributes, the number of attributes and their relative percentage per stage. And you can see in this scheme that there's the floodplain system, the stage 0 and the stage 8. They have really big bubbles and lots of diversity of attributes. They're rich, ecologically rich river states. Compare that to the incised, the channelized, the incised, the arrested, the degrading states down here. The bubbles are really small and they don't have very many attributes. A lot of difference between those two. They're not. Plot that up in XY space with the hydrogeomorphic attributes on the x-axis, habitat and ecosystem benefits on the y-axis. Several things emerge. First of all, here in the yellow area clusters all the really poor performing channels. Range of providing habitat for each. Green field is the really high performing channels, and these all have access to and frequent one type of channel that lands a little bit in between, and which is I guess it's the latest man-made channel. restored meandering stream with a nominal floodplain, but we're almost always building remeandering streams to some perfect geometric form, bank stabilization, with grade control, and with floodplain inundation at the 1.5 year. So in conclusion, the level of habitat and benefits is irreplaceable by channel enhancement. You can't enhance an incised channel to get anywhere near the habitat and ecosystem benefits of a floodplain stream. Only floodplain processes provide the high level of benefit. Low benefit streams can evolve given space, given time, encouragement. We can recreate floodplain in incised channels. Seasonal and perennial wetland floodplain complexes were historically common features in alluvial valleys. So some observations. Most of today's alluvial streams are the result of past management for flood control and land drainage. They were focused on making sediment transfer zones and quick drainage. Our history, our brief history of managing rivers for habitat is very short, and it's biased by the preceding 2 centuries. Mentally changing their physical work. I have a few suggestions, and then I'll turn it over to Lauren. We should start managing for process discontinuities. If you think the out that comes in does good, checkbox. Wetland floodplain system, if we do it. Sediment as a resource, we view it as a pollutant. That's kind of crazy. Sediment and water are all there is for habitat. And we need to reevaluate stability. A stable ecosystem is unrelated to a stable channel. Thank you, and I guess we'll take questions when Lauren's done. So.
Okay, are you all converted to the benefits of complex wetland channels? I hope so. I'm going to go through a couple of examples and get down to, okay, where is it realistic that we can find remnants of these, where they might be actually restorable given all of the changes that we've wrought on our landscape here in California, across the West, but particularly here in California. Give you a couple of examples where we're finding them and how they're being passively restored and somewhat actively restored. And I'm going to focus my talk on the River-Estuary Ecotone because that's where we're finding them. There are other locations, as Brian mentioned, that area number 1 up in the upper watersheds, up in the mountains, out here in the Central Valley area. Other people are working on looking at wetlands in these zones. I've been focusing my efforts out on the coast. And so I'm going to go through a couple of examples. And so you get to see what they actually look like, all of these attributes and values that Brian talked about. I'm going to start with Willow Creek, which is in Sonoma County. It's the first tributary of the Russian River up from the mouth. And this watershed and the work that's been done in it and how the channel has converted to a and it's given those of us who work in this area a lot of sort of food for thought. Watershed was, the lower section of the watershed was first purchased by state parks in this, I believe, in the late 70s. Upper watershed has been primarily owned by timber companies. So it's big chunks of open land. Last 10 years, I think it's 90% of the watershed has gone into fee ownership. Watershed that has a lot of land. It's had a lot of heavy land use over the years, but yet it has opportunity, and it's in this. So what we're going to show is some channel conversion from that single thread channelized stage 2 that Brian was talking about to a multi-threaded stage. Passive restoration. It's been fun to watch. We don't usually get to see channels convert in our lifetime. Usually these geologic processes occur over hundreds of years, and we don't actually get to see them. So as geologists, geomorphologists, it's been very exciting to watch this occur within 20 years. So, we're going from this stage 2, you've just seen this graph, up to a stage 0 in lower Willow Creek. Of the watershed is like most of those throughout Northern California coastal watersheds. Upper timber areas were heavily logged. Willow Creek actually has the first logging permit in California was granted to Willow Creek. Huge redwood trees shipped out, taken by steam donkey right down the creek, on trains, hauled to San Francisco to build the city. Multiple series of logging practices over 150 years, including going through and second growth clear cutting. Extensive logging in the upper watershed. So what does logging do? We all know it brings a lot of sediment down into the watershed. This is also on fault lines. We've got the San Andreas Fault just offshore, steep, lots of landsliding. Get the picture. The lower watershed, these alluvial valleys, they were settled early. In fact, the Russians, when they went to Fort Ross, they actually had a satellite community in lower Willow Creek. So they started clearing Europeans. This was one of the first valleys that was probably earliest cleared in California. They settled in the lower alluvial valley. They put in farms. They manipulated. They drained the lower wetlands. And that continued into the 1960s as cattle farming as well as hay fields in the lower watershed. I do want to bring you attention to a couple of sort of sites or places that you'll hear about as I move through this. This is the lower Willow Creek Valley that we're going to be talking about. We've got 3 bridges. One is right upstream of the mouth, just upstream where it comes. Second bridge here, and then third bridge. Those sort of brackets. So what I just described as land use practices is very common in all of the coastal tributaries. Also somewhat to the south. So it's common. So the geomorphic responses and practices that you'll see are very common to those watersheds, which are critical for salmonids, for independent and dependent. Now, this is what channel dredging looks like. Let me go back to this. The channel, to maintain those valley floor fields and crops, they actually channelized Willow Creek. It was on the left side of the valley. They moved it over to the right side of the valley, channelized it, kept it under, took it out through the wetlands, tried to keep sediment and flow moving as quickly as possible through that area so they could maximize their field. Dredging look like? They would have to dredge this probably about every 10 years is what the record shows. Last dredging was done in 1983. They could certainly get up through it, but it doesn't have any habitat value. 1984 in the Russian River area. In 1986, we had a couple of huge storms. Russian River backwaters, Willow Creek, high flows coming down Willow Creek, it would evolve and splay gravel into those fields. After state parks took over the property. And they decided that in 1984 that regularly dredging the channel was not part of their state park. So over the next 20 years, what has happened is because the Russian River backs up, and it backs up all the way past Second Bridge during really large storm events on the Russian River. So what happens when you've got high loads of sediment coming down out of the upper watershed is it deposits on the floodplain, it deposits on the fields, it starts filling up the channel. In the migration of the channel filling, as you can see in this graphic, up to that location. Illustration of that. Successive year, high gravel loads coming down, it fills the channel, you lose capacity, it splays gravel over, channel networks, the water spills across the valley floodplain, alders start growing in those fresh gravel deposits. Start getting these smaller channels flowing through what used to be an old hayfield. Photos. This is 1987. You can see all the recently active hayfields, no wetlands. By 1999, we start to see wetlands forming up here, alder stands. Larger tracts of forest and wetland as it moves upstream. Up till now, we've got wetlands and alder forests almost all the way up to Third Bridge. That's about 2 miles. What's happening here is we've gone from a stage 2 channel this channel would dry out. You'd get fish moving up it and moving down it, but you really wouldn't have any real habitat value within that valley, which is where all the critical habitat was before. Now we've got all of this food source, all the biomass associated with this wetland vegetation. Lots of songbirds and food source for juvenile salmonids. At that point, we actually weren't getting any salmon into the watershed. And I started on this project in about 2002 on a project that had already been defined, which was fix this valley. We need to fix this channel. We want you to design a single thread, self-maintaining, bank-full, fish-friendly valley. And I took that on, and pretty quickly I realized, yeah, we could put one of those in. You can always design something like that, but how long is it going to last, given that we've got high sediment loads coming into the watershed? And we've got the Russian River that's backwatering up, and if we take all that sediment that's coming from the upper watershed and shuttle it directly down into the tidal wetlands that are in lower Willow Creek next to the confluence, or even down into the Russian River, where's that sediment going to go? Is that going to be valuable to those features? This valley, it's designed to store sediment, that's how these alluvial valleys form. Why do we need to put in a single thread channel? Salmon hadn't been seen, both either steelhead or coho, in this watershed since the mid-90s. Pretty typical for this area. Fishing and just cumulative impacts. But we realized that, and yet the upper part of the watershed, the upper channels, were really great, typical spawning habitat. It's all redwood trees, huge log jams. There was no reason that coho shouldn't be thriving in this watershed, and it was a high priority watershed for the coho recovery plan as well as the. So we're not getting fish into the watershed, even though there's all this high potential. As you can see, and as you've heard, the sediment was filling the channel. The actual old historic bridge was no longer. Most of the water had moved over to the valley fallway, which is where we've got this old culverts were the second bridge. The road transected the floodplain. Fish were no longer able to get up because of water sheeting over the road. And so what we ended up with the technical advisory committee and about 10 years of decision making, a lot of discussion that went around is that there is in other areas that have these same issues. Channel, do we put in more bridges? How do we deal with the flooding and all of the infrastructure? And with putting in a bridge. Put in a bridge, and there were still some questions in the fisheries community as to whether, because the coho, the broodstock program actually wanted to stock the watershed with juvenile coho as part of their recovery. Questions still lingered as to whether there were channels that were connected through those wetlands. Will the adults be able to find their way through that network? And certainly, will juveniles, if we do stock this watershed, will juveniles get lost on their way? A mile and a half of just chaotic wetland channels. You all hear about juveniles, that these areas are valuable to rear in, but will they actually choose to rear in the wetlands? Russian River Coho Broodstock Program, as part of the project, started setting up a monitoring program. And they have put in a flat plate antenna at First Bridge, right at the confluence of the Russian River. And there is a third bridge. So we're documenting what fish come up this way and out at the mouth, and what fish come from the upper watershed or up from the wetland area, trying to monitor the actual wetland. At least the upper pit tag was set up immediately. Trying to find a location for the lower flat plate took some time, and they actually had to have a special flat plate antenna. So this is evidence that this is red monitoring adult steelhead and coho, where they've laid their eggs and where they've gotten up to, and they do adult fish counts, spawner counts in the winter. Immediately upon the bridge going in 2011, there were wild fish that were found up in the upper watershed. First, we had early rains in 2011, I think in like right around October 15th, which was a nightmare for construction, but actually got fish right up the watershed. They've been continuing to up, and every year we see more and more spawning activity in the upper watershed. As for juveniles, the broodstock program plants juveniles both in the fall, and I think it's most so that the juveniles can choose to rear in the upper watershed or move out. So we have both wild spawned juveniles in the watershed as well as broodstock. Stock juveniles are pit tagged and track their movement in and out of the watershed. So 2013, 2014, this just shows how the upper slide is how many fish and when went past that upper array, when they moved out of the upper. Nice bed and banks, pool riffle, redwood, overhanging dense vegetation. And they moved out of that environment and down into the wetland, and then out. The bottom graph shows when those same fish moved out at First Bridge. So the question of whether they're getting through, we got typically 80. Maybe they didn't see them, and spread out, and then they cluster, leaving the wetland end of number of days that they stay in that lower wetland zone. Many of them, especially if they leave late this year in 2014, only spent a couple of days. Some that left earlier tended to stay longer, up to almost 3 months. Many right around, or 2 months. Many stayed about a month. So what are they doing in that wetland? You think they're feeding and getting around and taking advantage of all that food source that's down there. I do want to say that since 2011, we haven't had a good water year. 2011 was a great water year. It was wet. We got lots of late rains. The valley was wet, 6 inches deep. Haven't had that since then. So we'll results and fish utilization. So the answers that we've gotten so far after 3 years of monitoring, yeah, the fish make it through the wetlands, and a few probably get lost on the way out, but that's no different than if you had a single thread. They choose to rear in the wetlands, probably more likely in wet years. When we had to de-water to put in that bridge, and there weren't water to put in the bridge, we actually found why we were finding young of the year coho that are about long. That's huge for young of the year. That was Willow Creek. We're continuing to monitor that. The coho broodstock program is committed to that. It's a bed for recovery, salmon recovery in the Russian River. Started on a couple of other projects that are located in similar environments. Just started last few months at looking at the lower Garcia River in Mendocino. Garcia, the majority of this property is now in BLM and has become one of the lighthouses. Beautiful area. One of our study areas is Hathaway Creek. You can see it's located geographically very similar to Willow Creek. First tributary had extensive modifications for agriculture. These are dairy and beef cattle farms. They also raise crops, row crops in the spring. So this is the 1942 air photo blown up of that Lower Hathaway Creek. This is Highway 1 here. So Lower Hathaway Creek, you can see in the 1940s, this line here, they had just literally just blasted this new channel into the wetlands. That looked like wetland, classic reclamation of wetland areas for farming. So dig a ditch, drain it, put in your fields. Now this is 1992 infrared. This line here is where that ditch is, and sure enough, if you go out there, there is a ditch that's about, I don't know, 4 feet wide, 5 feet deep. Question is, what's in here? This area, this is in the monument, and so what is this dense willow thicket? You can't even walk through there. Nobody knows what it looks like. It's tough to find out what's in there. Are fish utilizing it in that same way? Is it a wetland channel? Our projects, and this is with the Nature Conservancy, have LIDAR, and this is graphic data. The dark red shows deeper elevation. That ditch was, or is, that's draining the can't see, and it looks like there's all these low areas over here, very hummocky, wetland-type features. Berm along all of these little levee, so you can't active restoration. If we can get reach this levee that's along here and get water over into these areas for juveniles to utilize. Third example we've been working on in the same ecotone, also with the Nature Pioneer properties that they've got conservation easements on and are working with the landowners to do ag. Once again, lower valley is all ag, upper watershed is timber harvesting. Did a lot of our work on the South Fork, which comes in here. And I'm going to go through this quickly. This site does not have a lot of those wetland features. It's had a lot of sediment come down over the last 100 or so years. The channel is aggraded. It's no longer connected to its floodplain. It probably floods on the 10, 20 year. What do you do in these environments where you've got a larger channel and you need that sort of flooded wetland habitat for juvenile salmonids and others? You start doing what you can, putting in off-channel ponds, excavating flooded wetlands, getting large wood structures in so that you can start. That's what we've got going on here. This is, and represents our conceptual design for the reach. Work being done in this estuary ecotone. Why, just quickly, why this is so important is that coho recovery and coho success, not just coho, but all salmonids, it's really about growth, and it's really a numbers game. That's their strategy, that's their evolutionary strategy, is to a lot of eggs. You're going to have a lot, there's a lot of loss between life stages as they move down through the channel, trying to survive in high velocity environments over the winter, dealing with predators, various hydrologic and hydraulic events, flood events, washing out reds. They need to produce a lot of eggs and a lot of smolts. The more smolts that you produce and the larger those fish are that go to the ocean, the more likely they are to return. So as you heard from Brian, on these straight and narrow channels that are incised and don't have a lot of habitat value, if you don't have feeding opportunities for these juvenile salmonids, they don't have the opportunity to grow large. They're unlikely to be able to be successful once they get out to the ocean. So how do you create a lot of fish, and how do you create fat fish is really the recovery key for our salmonid populations. And Sean Hayes from the NOAA Fisheries Science Center down in allowed me to use these slides of his. He's been studying steelhead down in Scott Creek, and those are the sort of results he's come up with, is that this estuary ecotone is really important for salmonids. It's a dangerous environment, especially for steelhead that are moving around in the open estuary. There's a lot of predators there. So the survival, once they move from the upper watershed down into the lagoon, there's a lot of loss, but yet the growth potential in this area is really high. And he's finding that in this altered environment where that estuary and those interfaces between the stream and wetland floodplains have been disconnected. So my premise is that if you can get some of these flooded wetlands restored, that survival curve that you see on this graph in the lagoon is not going to take such a steep dive, because right now those losses, some of those losses are just due to those fringe habitats that are no longer available, and those areas just outside of the estuary that are flooded wetlands that are no longer available for the juveniles to go and get out of harm's way, so to speak, and put their growth on. So Sean has a fun little quick illustration here of if you just go down the straight and narrow channel and you go to the estuary lagoon interface ecotone and you don't have a chance to feed one fish, a redfish. And you have the same population, and there's a percentage of the group that decides to go down to the estuary and the flooded wetlands, and these little graphics illustrate food, which is reward, and predators or other types of danger that is risk, which are higher. Both of those are higher in these flooded wetlands and estuaries. Go down there, you hang out, you grow really fat, you lose a bunch of them, but yet you survive in the ocean. So he's finding that even though the 20% of steelhead that move watersheds and move down and use the estuary lagoon, 20% of the population decides to do that, but those that do that and they grow large and they go out to the sea, they represent 85% of the fish that are returning to spawn. So, and you get lots of bluefish. So I think I'm going to quickly wrap this up so that we can move on to questions. So we've got juvenile rearing. The lines across the top here represent months: January, February, March, April. Biologists have got this logged in their heads, but coho rear after they're spawned in the upper watershed or down in these. By year, they're probably not going to go down there in the summer. They do explore around the following year in out migrating in February, March, April, May, sometimes. When they're out migrating, this area is key for them to put on some weight if they've been in watershed waiting to leave. Had come down, they spend several years, they hang out in the estuary, in the open water, they migrate around seeking food. That's one of their strategies. They may not use these flooded wetlands as much, but if we have them, then the coho can critical area for ecosystem all of that information, a couple of photos of what flooded wetlands look like, multi-threaded channels in Willow Creek, and other critically endangered species such as frog and a really big coho. We're open for questions now. Thank you.
So I'll come around with the microphone if you have questions, and this is so the people on our online audience can hear your question as well.
What was the stream gradient your model's designed to use?
Well, it includes everything from the flattest alluvial valleys to the steepest alluvial fans. So it really covers a wide gradient. The habitat and ecosystem benefits portion of it is most directly applicable to the low gradient alluvial valleys. But really one of the points is it's not about gradient, it's about how sediment is processed or managed. It's either sent further downstream to do harm in some more sensitive environment, or it's deposited and temporarily stored and sorted in a natural environment. That's why the steep alluvial fan is really an important multi-threaded channel subset of the model.
But if the natural environment is, say, a canyon stream with a significant amount of gradient, wouldn't it be natural for sediment just to be generally moving through?
Yes, it is. And so the incised channels are representative of the natural canyon sections. So, you know, where we've created incised channels, we've basically just replicated what you would find in nature in a canyon channel. It doesn't have capacity to store and sort sediment. It just moves through. Those are continuity channels or regime channels. So it covers, I think, the whole range of naturally occurring gradients.
Question for Lauren. Both of you guys, great talk. So I'm curious about the 20% utilization of the, was it the floodplain or estuary? I don't remember. Could you describe a little bit more of the dynamics, whether it was hydrologic or spatial or temporal related to that only 20% use there when you described Sean Hayes' work?
Right. This is just my understanding from Sean Hayes' study on Scott Creek, where he was tracking steelhead in Scott Creek. And this is approximate, I don't have everything memorized, of course. We'll have to ask him for more details. But my understanding of it from talking with him and seeing his presentations and talking to other fisheries biologists is that both steelhead and coho, and maybe not so much Chinook given their life cycle, is that within a population there's different strategies that different individuals take to survive in the watershed. A percentage will decide to stay up in the upper watershed, and a percentage would decide to go down to the estuary to rear. Whether that's density dependent or whether it's embedded in their genetics, I don't know. I've heard that there's different phenotypes within an individual salmonid population, that they would choose to use different areas as different strategies. It's sort of the whole species approach to survivorship is to spread your juveniles out around the different watersheds in the different rearing habitats. So my understanding is that what Sean was seeing was that 20% of the steelhead in a given year's juveniles would choose to move down and rear in Scott Creek estuary. And he was tracking many, many of the juveniles in a given year. So 20% of those he was tracking would go down to the estuary and rear. So he had the genetics on those. then all the fish would go out to the ocean as smolts. Those that returned, the genetics of the adults that returned, 85% of those came from the fish that had gone, the 20% of their peers that had gone into the estuary.
Great. Yeah, that does. Yeah, thank you very much.
Yeah, that work was based on otolith studies. So, you know, it's like having a flight data recorder in a airliner. You can tell where they spent time and how valuable the habitat was during that time.
I would caution to that last point that we really should look at each system separately, because you need to make a distinction between open and closed lagoons, so that we found that in some cases closed lagoons, you know, barbell lagoons that create a substantial freshwater lagoon, can be really good for production, both numbers and growth. So I'm not too familiar with Scott Creek, so that might be an open system. So let's not overgeneralize.
Yeah, that's a good point. Between open and closed, there's vast differences. I think Scott Creek is a closed system.
Brian, you stated in the beginning that these systems were far more than just a system of channels. Are these valuable ecosystems that are more than a system of channels and beds and banks currently protected by a Department 1600 program?
I don't know, Corky.
You don't know? Okay. Do you the Streambed Alteration Act?
Yeah, I'm not that familiar with it.
You're not? Okay.
Somebody else want to field that question for me?
I mean, you're talking about the value of them, so the question I have is, are they protected?
Protected for conservation.
From building and...
Well, are you going to try to answer that?
Yeah, I'll try and answer it. Since I'm from the department and you're from fisheries, yes, they are protected under the 1600 program.
But it's pretty limited, isn't it? It's the bed and banks. It's the floodplain is like private property. That's not protected.
Actually, it depends on, it's kind of a context-dependent situation, and, you know, it's always good to get geotechnical borings or that sort of thing to see where the hyporheic zone or the subsurface flow is, and also looking at if there's associated resources that are supported by waters of the state, then those can also be folded into being protected also.
You got me on that one, Courtney.
Great talk. I imagine that the project, in order to get FRGP funds or any other funds, that the area of the project would be put into a conservation easement or something like that. So was that kind of the point that you're getting at? Once you do the project, is it now protected, or can someone go back in there and, like Willow Creek, and dredge later? But that one's a state park. I think I went on that tour, and even last spring we were surprised how high the water level was, even in that dry year. It was topping in some parts of the road, even in the drought years.
Yeah, correct. It is, from my perspective, trying to find and working with clients and restoration entities who are looking at areas and getting really interested in these types of habitats. for restoration and protection. It's really trying to find locations that they can be protected, which is why Nature Conservancy is doing such a great job of getting conservation easements in these zones where there's state parks. That's why I focused on the ecotone that's in the estuary and riverine interface, because there's more space there. There's typically more space. Agriculture isn't as economically viable given the climate and the fog and the cold, and so there's space.
You're getting your exercise.
Yeah.
Yeah, so moving to places where agriculture is economically viable and thinking about how to reconcile this model with ongoing agricultural production. So thinking kind of yellow bypass ideas, maybe compatibility with annual crops or perennial crops. Has that been at all explored?
That certainly is being explored in kind of an experimental way near the Yellow bypass with the Nags Island project that Jacob Katz and others have been working. I'm glad you brought that up. You know, any cursory Google Earth fly-through of the Central Valley shows you that there's still hundreds of thousands, if not 1 million or more acres of what we classify as wetland, and it's owned by either the state or the federal government. It occurs to me that those are tremendous opportunities. The problem is they're not connected to the stream. They're disconnected. They're maximized for, for birds, and they're minimized. They're actually disconnected from their ecosystem. So I think there's probably a lot of opportunity in the remaining hundreds of thousands of acres of Sacramento Valley, Central Valley wetlands to put them back into salmonid production as well. And we ought to start exploring that.
Yeah. And as far as benefits, potential flood control benefits of that sediment deposition upstream and protection of higher value areas. I was also thinking you discussed the sorting of sediments and potential for agronomically beneficial sediments to be mobilized and perhaps placed on agricultural land in a strategic, slightly managed way.
You know, the source of all of our soils is floodplain deposits. And somehow we're continuing to have economically viable agriculture without replenishing the natural material of our soils. I guess we're doing it through chemicals and fertilizers and practices that, can keep those soils productive. But at some point in the future, we're probably going to need, for agricultural reasons, we're going to need new soils.
Yeah.
So looking at the hundreds of thousands of acres of Central Valley wetland, I can imagine a rotational scheme where, let's say, just to use some simple numbers, let's say there's 1 million acres of wetland out there now that's not in agriculture because it's too low lying, we couldn't figure out how to drain it adequately enough to farm it. And so we call them wetlands. And, we gave them state or federal designations. Well, you could reconfigure those so that a portion of them was connected to the river and could become deposition zones. The Sacramento River, like pretty much every one of our alluvial valley rivers, is listed for sediment load. And the reason for that is not so much the sediment source, is that sediment has nowhere to go. Once it's in the river, it stays in the river because there's no deposition zone left. So we could really improve water quality, for example, by recreating deposition zones in our alluvial valleys. Those deposition zones could evolve over time to become less engaged as floodplain as they their elevation grows, or as they keep up with subsidence or sea level rise, maybe they just continue to be deposition zones. But it seems to me that, you know, we could have a rotational scheme of deposition zones that are really rich salmon habitat, wildlife habitat, that ultimately get converted to farming, while another part of that low-lying wetland area gets reconfigured to become the new deposition zone. Those are sort of big picture, really big picture ideas, but that's kind of how it works in nature, and one way or another, we're going back to that scheme because sea level rises and the land subsides.
Thank you.
I just kind of wanted to make a comment based on the last questions, and I've kind of been thinking with what needs to happen in the Delta and what DWR is doing with their islands and with greenhouse gas mitigation money going to, and they're looking at farming rice now in some of the subsided islands that will may not reverse subsidence, but it will perhaps stop it. And you're talking about deposition zones. I mean, all these things kind of start layering on each other and start making for, you know, actual kind of multi-benefit spots and islands that DWR owns in the lower end of the Delta. And tie that in with the pumps, if you will. You know, if you're flooding these islands and we're trucking fish, why can't we truck them to these now flooded islands we're growing rice on and then pump them out with Archimedes screw pumps, or there's other pumps that have been tested that have very low mortality rates on fish. I mean, when are we going to start kind of acting on harebrained ideas like this that just might work?
I think those are great ideas. The experimental work I'm seeing coming out of Sacramento Valley on salmonid growth is just really encouraging. I think there's some institutional impediments that need to be worked through, and we just need to get those conversations going.
I just wanted to point out that we did have a talk in the conservation lecture series probably within the last 6 months on just that concept. It was in the Willow bypass, and I think one of the pictures that you had there was showing the growth difference between the ones that are in, you know, the Sacramento River versus the fish that were grown due to, I guess, flood manipulation in the Willow bypass and the growth of the salmon. And so there is a lecture that should be on our website that you can go and watch that. I believe it's probably a political decision why it doesn't expand more so.
I was just wondering, this seems like a very efficient way of restoring. You don't have to do a lot of manipulation. But do you expect these ecosystems to remain stable in the sense that they continue to be great salmon habitat, or do you think it's going to require some kind of intervention, maintenance to retain them as this habitat?
There's actually a couple of things that you said. One is it's great that it seems like we can more passively restore. And I think the ability to passively restore is only present in some locations. Actually, because we've entrenched our channels so deeply and cleared them of all obstructions that would lead to sediment deposition, like wood, essentially, or straighten them so that they don't have any migration and there's no outward bend, erosion, etc. There are, in many alluvial valleys, we actually have to go in and be much more active in the restoration, and that's the 10-mile example that I gave, where those alluvial valleys have been so disconnected from their floodplains that we actually have to go in and to create some of this type of habitat, we have to really manipulate, and that means moving a lot of sediments, either lower the floodplains or put in a lot of wood, not just our little habitat structures here and there, but a lot of wood to actually start blocking the channel and creating situations where more wood will be trapped and thus creating an aggradational environment. So there are areas that can be passively restored. And probably a lot of the delta can be, and the Central Valley, because it's been diked off and levied off. I'll let Brian give his thoughts after that.
Yeah, my thought on that question is it's a matter of scale. So, you know, we see projects that build what they call a floodplain that's sometimes just a fraction of the width of this room. Well, that's not a floodplain. But if you're talking about the whole valley width, like Willow Creek is, small valley, but it's engaged with its entire valley width. The width of that valley makes it so it has such a capacity to receive even incredibly anomalously high sediment loads from its faulted, logged, crisscrossed with roads watershed upstream. It's got one of the highest sediment loads in the region, and yet it's going to persist because the sediment that caused the problem when we had a single thread channel and resolved its own problem through passive restoration of filling its own channel and causing avulsions throughout on the valley, it is now creating, perhaps you think of it as a very low gradient alluvial fan that is marching its way up the valley. And it's got a long ways to go before it runs out of space. And in that fan that is received, that's marching up valley and is receiving the coarse sediment stays there, and only the finest sediment makes it a little bit further down. And no sediment at all is getting through the system under most conditions. So it's remarkably resilient, and I expect it will persist for millennia, even in a highly disturbed watershed.
If there's enough space for the channel to do its work, whether on any floodplain, if it has enough space, then if one area becomes less viable for habitat, for salmonids, another is available. So if you're constrained and you have a big event and you fill it all in, or something happens and there's not enough space for it to work and shift. So in some locations there's probably, you would need to do some maintenance, but if there's enough space then it maintains itself.
You might look at this upper left photo here. This is in Willow Creek, and this is currently the dominant channel. It's in places maybe about 3 feet deep and no more than 3 feet wide as well. And it is flanked out here in the alders and even in this grassy area. It's flanked by minor channels, a network of them. I really think of this more as an island network than I do a channel network. And so if, let's say, a few alder fall into this dominant channel, or a beaver builds a dam in its dominant channel, or a landslide comes in from the side of the valley and floods this dominant channel, there's a whole series of additional channels that can then become the new dominant channel. And so the habitat will always be there. It will be ecosystem stable, but it'll be very dynamic at a location.
Yeah, over here. I was wondering, in any of these, the projects you're working on or have shown here today, if you had to deal with infrastructure constraints regarding flood risk, and if so, how you handled that, like people's homes and such, because a lot of us deal with that sort of issue.
I've been lucky to have avoided those sort of concerns in these 3 particular projects. I deal with those concerns on a lot of other projects, which, you know, limits what we can do. In many of those projects, yeah, grading the channel is not an option unless it's coupled with creating some floodplain too, which is excavation. So if you've got some space to work with again and some money, you can create more of these types of more high value in-channel floodplainy type habitats, but you need to have some space. And so they do tend to not work in an urban environment, although I have been working on trying to get a few.
So then are you saying like in a smaller scale area that's more constrained, that creating sort of a balance, so to speak, like if you're going to grade an area or calculate how much, then maybe downstream or some other spot you can figure out how much needs to be removed to compensate?
Right, or adjacent. To create like a multi-threaded channel, you would need to get some space. You can maintain and then lower floodplains within. So it's moving it more towards the stage 8 channel. I'm going to go back to that quickly. I should have just turned this off, but let me just go back quickly to that graphic of Brian's. See what that looks like, because that's exactly what we're talking about. So if you can get space within an incised area in an alluvial valley that has constraints nearby, and you can get enough space to get this sort of inset wetland channel and still have enough channel capacity, or mimicking flood protection that's already there, that's a possibility.
Yeah, but it wouldn't be the best strategy. So, there's places where you can make investments in floodplain that will actually perform as a floodplain, and then there's places where you can create a nominal floodplain, even in an urban environment, but it's not going to perform like a floodplain that has a water table, that has successional vegetation communities, that is doing carbon sequestration. It's just not going to perform. That's what that stage 6 channel is like. You may not have it here, but it's just sort of the idealized, remeandered, semi-urban channel that has great stabilization, hardened banks, a floodplain that gets wetted for a few hours every year and a half, and it just doesn't perform ecosystem function. So it'd be a bad investment. It would be better than riprap lined channel, but it's if you've only got a certain amount of money to spend on ecosystem restoration, that would not be a good investment.
I was actually thinking more of an instance where somebody living in a more rural area is highly concerned about large wood in stream on their property and how to kind of keep that or alleviate their concerns in a way.
Right. The general population is generally concerned about bank erosion. And I bump up against that all the time. And it's slowly changing, depends on where their infrastructure is. And really, it's just like education, just like anything else, having, heart-to-heart conversations with them. Talking about value and fisheries habitat and how attached they are to seeing salmon return to our watersheds. And I've had those conversations in watersheds that I've worked in for 20 years now, and it's come around. Started off with no wood, we need to dredge. All the fish were here when we were regularly taking the D8 cat down these watersheds and taking out the willow, and that's when we had fish. And, just talking and talking and talking, and pretty soon they're allowing wood, and they're allowing projects and they're giving up space and setting their fences back, and it happens. It doesn't happen overnight. It just takes time.
That question was one of the motivations for me writing this paper, is to give you all arguments for why space is a critical part of a functioning river ecosystem. It doesn't occur in the channel. All those processes occur outside the channel. So that session that we convened at SRF, that you invited Lauren and several others from that. The title of that session was Beyond the Thin Blue Line. And the meaning of that is, when we look at streams on maps, they're depicted as a thin blue line. But so much of the ecosystem function of a stream occurs way beyond that thin line.
I don't know if you could answer this question, but how have recreational activities gone up in these restored areas?
Well, so for Willow Creek, converting from open dry fields to that wetland marsh, it has become one of the top birding destinations in Sonoma County for songbirds. I like hiking around in it because I get to see bobcat tracks everywhere, but not everybody wants bobcat and mountain lion in their backyard. So, educational hikes through there. We've got some spots in Sonoma County where you can hike through wetlands, and people like to wander through them. They've got interesting vegetation, and certainly not good for kayaking or rafting.
Hi, you guys. Back in 1976, in Winnipeg, Canada, I gave a paper on whitetail kites, and my major prof was Nicholas Diafood-Barty. I don't know if you've ever heard of him. He's a well-renowned biogeographer and ornithologist, actually. And he told me when I went up to give this paper, and he said, "Oh, one thing." He said, "Be sure." This is 1976. He said, "Be sure and close your paper with a comment that man will have to be involved in management of everything when we go in and change things and when we try to put it back." And as it relates to us listening to you guys talk, and we do restoration projects, but we can never walk away from them, can we? Do you have any comments about that?
Yeah, the most common restoration projects, just by sheer numbers, are stabilizing banks. And those always give out at some point. Just in my short 15 years here in California, I've seen some of the same river banks restored 3 times. And yeah, it seems like, stabilizing property it's an ongoing thing. We have too many expectations for stability. We're living too close to the edge of the banks. They're too steep. They're too high. They're geotechnically unstable. And no amount of willow on them makes them geotechnically stable. They're too tall and too steep. So understanding why allowing stream banks to fail to a gentler slope and taking up a little more space is in a landowner's best long-term interest and in the fisheries agency's best long-term interest in terms of habitat and expenditure of money is part of the reason for writing this paper. We can't keep going back to the same places and really not getting much ecosystem value out of it anyway.
Going back to the Central Valley, my understanding is that there's much more of that remaining de facto wetland habitat in private hands, like rice rice fields, in agriculture, and that the state and federal wildlife refuges is a lot smaller amount. And one thing I have a concern and caution about is, I see that you can get this good growth in these rice fields and stuff, like the salmon you showed. But what I worry about is those are very simplified systems compared to a natural wetland. So if we get good production but very poor survival because you have much less complex cover, they may end up being a de facto survival bottleneck. So, if you were to, as you suggest, with some of the, say, a national wildlife refuge, how would you kind of move your ideas forward? What would you suggest if we wanted to try to restore floodplain habitat on a federal or state wildlife area and maybe get more complexity?
Well, I've only visited a few of the wetlands, and they do have a lot of open water on them. But I think maybe they're managed for that. I think they manage them to go through cycles of desiccation, and then they pump them full of water when they want to, in order to keep the vegetation growth controlled. So that's one thing you'd have to couple vegetation cover with your connection to a river, increase survival. But is it known that there's poor survival in even these open, barren rice field experiments?
I don't know. That's what I'm asking, but that's my concern.
Yeah, I've spoken to Jacob Katz at length on this, and I think they're showing very high survival rates on those barren, just tilled rice fields. In fact, they did some experiments this last winter on different field treatments to look at survival rates. They plowed some plots, they left stubble on some plots, and they had a third treatment as well. And I'm pretty sure that the survival rates are all about the same.
But for the rice stubble, I would think that they'd still be very vulnerable to predators like.
Well, the water clarity is really poor, and so they're hiding in unclear water, and it's poor because it's so full of zooplankton. It's full of food. They're hiding in their food.
Relative to a historic situation where the vegetation might have been tules or cattails
Right.
day high,
Right.
I'm thinking you could have had the same growth rates perhaps, but even much higher survival. That's what I was trying to get at.
Yeah, I'm sure you're right. Predation's got to be some measurable component of loss out there in the wide open waters. But I'm not the expert on that. We should check with Jacob and his colleagues. I don't think they're seeing predation really taking a toll on those wide open growth experiments like you would expect it to.
Well, we're at just about 3 o'clock, so we'll cut off if there's any more questions. Thank you both so much for being here and for all your great information. Thank you.